All right. Okay. Thank you, everybody, for joining today. We have Professor Roel Vertegaal from Radboud University in the Netherlands, who will be presenting on interactive inference, a simplified active inference account of interaction. So over to you, Roel.
Hi, everyone. I'm Professor Roel Vertegaal. I got started working on active inference about 3 or 4 years ago when I was working with one of Carl's postdocs, Zaf Fountas, um, thinking about what this theory might imply for my field, which is not uh, neuroscience. It's actually about designing stuff for people using computers. It's called human-computer interaction. So we're the guys who invented the mouse and touchscreens and all these other gadgets that you use today. The problem in my field is that we've never had a comprehensive theory about how to design stuff other than the bits and pieces that came from psychology, such as Fitts law, Hicks law, and I'll talk a little bit about that. And it struck me that active inference would provide a much better fundamental basis for our field if we could somehow apply it, operationalize it, and make it so simple that it would be something that designers could use. So that's what I'll be talking about. Now, this talk isn't simple because I'm talking about some theoretical constructs, but I hope you appreciate that the math that results from it is. So I call this area interactive inference. It's basically a spoof on active inference where we're focusing on interactivity. So what we're trying to do is to see how the user's mind interacts with a computer system. And you can think of this as having observations that trigger hidden states inside the user's mind. And there's a Markov blanket between the two of them. So how can we improve the design of the system so that that goes smoothly is really the question that we're asking. And to do that, I have taken a look at physics. And it'll transpire later on why I did that. I think it had became apparent to me when you're talking about energy potentials. There are natural ways in which physics deals with them that we can actually borrow from physics, and perhaps we can actually use energy potentials directly and not even talk about things like Bayesian inference. So this is borrowed from people like Feynman and others who were very interested in using least action in order to explain the physics world and the energy and the way that that evolves over time. So this is about designing interactive systems using simple energy potentials with the objective of minimizing potential energy in stationary action, thus optimizing user surprise. And I say optimize because it's not always about the lowest or the stationary user surprise. As we all know, at the end of a Netflix show, sometimes there's a cliffhanger. And sometimes when you want to engage your audience, you actually create surprise in order to activate their brain. So it's about optimizing surprise, not necessarily minimizing surprise. Now, we all know that variational free energy is complicated. Expected free energy is even more complicated. I did do a good dive on it and made a nice Desmos model of maybe not the complete solution, but certainly the solution where it comes to finding a mean. So let me just show you what that looks like. Um, so here we see basically negative logs. And what we're doing is we're optimizing free energy. So what we're trying to find is first, the lowest point of free energy, which would be a negative log PO, and then we update the prior to the posterior, and we find another one, and we do this again and again and again and again until we hit the likelihood function, which is where the prior and posterior match, and we get to a particular negative log PO. And of course, negative log PO is the big question mark in this whole story because it's a normalization factor that we don't know in the Bayesian equation. I won't go into details, but what I will say is that if we look at this energy function here, the red one, we actually see that if we want to do a gradient descent on it, which is what we're doing, the actual elevation of this function on the y-axis is not all that important. The other thing I'd like to show is that as we update If we look at this point in that's the least action point here. If we update, we see that this point follows another curve, and this curve is actually very, very related to the negative log likelihood, which is what we are ultimately updating towards. And we can simplify this whole process by talking about optimization towards a negative log likelihood, and that is one of the big simplifications of this model. All right, so complicated. We want to make things simpler. First of all, operationalize variational free energy into real-world signal-to-noise ratios. And we do that through a thing called normalized error. I'll explain later what that is, but the idea is that if you can turn something into choices, then actually you can use the same energy potentials in order to find a solution, because all you're doing is reducing n number of choices to m number of choices. It simplifies variational free energy into one physics equation, only one. And this is the potential energy of a Hookean spring. Now, this is significant. Why? Because the whole universe runs on the potential energy of a Hookean spring. It even appears in the Schrödinger equation. And so the idea that the brain would use such a potential in order to do calculations is a very attractive one. We replace the negative log model evidence, that's negative log PO, with a threshold normalized error. So what we're doing is we're more or less ignoring this elevation on the y-axis, and we're saying, well, if we have a KL divergence, it's expressed on the x-axis with some kind of signal-to-noise ratio that we can use as a threshold. And this seems to follow the sort of more biologically plausible ways in which this is implemented in neurons. We model user action, and so we're not as focused on learning. I kind of ignore learning in this talk. We model the action using Lagrangians and stationary action borrowed from physics. And this is, of course, very close already to the gradient descent method, which comes from that area. So we ask, how do you point? How do you select? How do you decide? And then how that unfolds over time. And the idea is that if we can solve these equations, we should actually end up being able to model time behaviors as the energies unfold over time. And this simplifies expected free energy as well. And the way it does that, and I'll show that in a bit, is that we can use competing simulated action trajectories. So in the mind of the user, you simulate an action trajectory, this releases an energy potential, and the first to cross the threshold error is the selected action. And it's a really elegant way of sorting between many options where different means need to be compared. With this, we can calculate mental load, although I won't really talk about it because we don't have time. But in the paper, you can read about how we could do mental load by comparing relative information gain versus KL divergences that are derived from error. And what we see is that the two compete in the sense that there is an average relative information gain. If you get across that, which tends to be at a signal-to-noise ratio of 1, you start making errors. And we've done some experiments that actually show this. And then we'll talk about psychological models that this can express, such as Fitts law, Hicks law, and some others. So let's get started. First of all, what is a task? Well, a task, in my mind, aims to reduce physical entropy. You see that happening here. We have our socks everywhere in the home, and now they're neatly organized in a box, which means the entropy was reduced, but it also means I can find them where I think they would be. So it becomes predictable. And so to do this, you would then think that the brain also needs to reduce the relative information entropy. So i.e. the entropy of the information that actually processes this task. Now, I'll give an example. Maybe I've put my glasses somewhere, and because I'm not wearing them, I can't see very well. So I'm looking on the table, and I have like this prior thought as to where they might be, a prediction, if you will. But it turns out they're not there. And so when I look a little bit better, I see where they are. I'll put my glasses back on. And now I've got two things I can do. Well, first of all, there's clearly an error, and we can calculate this error as being the relative information between the relative entropy between two distributions. One is my prediction and the other one is where I should have been. And this is very similar to the kind of thing you see in the free energy principle, where we're looking at a prior and a posterior. But I want to state immediately that in my model, the role of the prior and posterior is rather fluid. So I tend to call the goal the prior and the update of where I am the posterior. But there's a good reason for this, but we'll get to that in a bit. Anyways, we have a relative entropy between these two distributions, which we call Bayesian surprise. Now, I can learn where my glasses are, or I can act and move the glasses to where I thought they were. In both cases, I end up with the next prediction being more accurate. And this essentially, in my mind, is the definition of a task where I have a goal, I have a certain progress of where I am right now, and really what I want to do is get to my goal. So here's a Bayesian model of such a task. So we see that the error, which is the KL divergence between these two distributions, disappears as I am improving my estimate of this Gaussian goal. Now, why Gaussians? I'm using Gaussians because they're so beautiful. The Gaussian math makes everything simpler, and it's a huge part in the simplification of the free energy principle to just assume that everything is Gaussian. It's a big assumption, but it's not necessarily a strange assumption, because in human perception, we tend to work with the means, and surrounding those means are Gaussian noise. So anyways, what we see here is that there is an error in the signal, which is the difference between the two means, and we have a certain precision with which I match the goal. So the only precision that matters here really is the goal precision. I want to make that clear because it simplifies everything. This is a noise floor. It's a standard deviation or a variance of the goal. This is not necessarily the same size as the entire goal distribution, and we'll get to that in a second. But think of it as the least discriminable unit of latent space. It sets the translation between the pixels in space and the bits in your mind. And we'll get to that in a bit. Now, important to say that I am using Occam's razor in this work. That is, we're using hacks that I've learned in software engineering and in physics to simplify things. One of those hacks is not just to assume that we're working with Gaussians, but that we're working with unnormalized Gaussians. This greatly simplifies the math because negative log PO, negative log model evidence, disappears. Physics does the same thing. In physics, it's called the Z partition function, and it is routinely ignored because it just troubles all the math. Potential energy relaxation of a particular kind, particularly that of a Hookean spring, approximates Bayesian inference. And so what's interesting about that is that we don't need to take a negative logarithm of a normal distribution in order to get something like free energy. We actually start with the energy to begin with. The brain lives in an energetic world. It computes energies, not Bayesian normal distributions. And that's because neural membranes can be thought of as a condenser. They are the capacitive analog of the potential energy of a spring. So if you charge the membrane, it actually acts very, very similar. And inputs are then modeled as voltage deviations from an expected state. And this allows us to, for example, have a voltage threshold. So voltage error can be normalized by the voltage noise, which then yields a simple dimensionless error, which we can use to calculate bits. This is important because there will always be a source of noise whenever you're calculating this on an analog medium like the brain. Therefore, we need to not just get rid of that noise by dividing by it, but what's even cooler is we're basically saying, well, how many noise steps, how many choices does the brain have, and that need to be reduced to an answer? And we can also say how many of these noise steps is the correct answer? What do we accept? The threshold voltage then replaces the negative log model evidence and emerges from task parameters. Now, this is a big assumption. What I'm saying is that if we use the x-axis in order to determine what error is good enough, then we don't really need to look so much at the negative log model evidence because it lives on the y-axis. And we also can see in many tasks, and this is specific to human-computer interaction, what the parameters are. So for example, if I'm moving my hand to a target, I know what the limited error is that I need to have because it's the size of the target, or some element of the size of the target. The optimization goal in our model is only the mean. We, of course, like to optimize the variance as well, but what we're saying is that we need to move the posterior towards the variance of the goal. And so we're only focusing on the variance of the goal. This hugely simplifies things. And the reason this is possible is because we can set the scale, i.e. the variance of the task, prior to a task, and then maintain that scale throughout the task so that it's invariant during the task. And this is an important assumption that really simplifies the math. This equal variance assumption means that potential energy is equivalent to Gaussian KL divergence. And this is really lovely because we just get an x squared function, and this x squared function actually gives you the KL and thus the surprise. All right, so why do we want that equal variance assumption? Well, first of all, when you approach an optimum, you tend to optimize over a square function anyway. And this is the Taylor expansion series. So near a local minimum, the negative log model evidence can be approximated by a quadratic potential. And near the goal, the first derivative goes to zero. That's the whole point of the variational optimization. And all these elements of the Taylor expansion series just drop out. What that means is we can isolate mean error. We don't need to do various bookkeeping, which is tedious, and it makes the prior and likelihood symmetrically interchangeable. It also makes the potential energy interpretation exact, which is really nice. And then finally, it removes the need to explicitly compute the negative log model evidence that I've said that before. So if variance is held fixed during the local update, unequal variance mainly changes the scale or stiffness of the gradient, not its basic Hookean form, okay? So this means we can still express things like attention or precision of a prior, but we do it before the task executes. Now, what happens to the KL divergence when you do this? Well, again, KL is a very complicated thing, but when you think about it, it's really just a subtraction of the two, the logs of the two equations, the two normal distributions. So what we can do if we make that assumption of equal variance is this just becomes the difference between the means divided by the standard deviation of the goal squared. So this is a really elegant equation, much more elegant than the case of the unequal variance equation, which you see in the bottom left here. But essentially, it is the same because the log ratio of the variances, that's just kind of a negative log PO thing. It elevates the entire surprise function, which is not really that important. And then we are left with this factor here, which is the variance in this case of the progress distribution or posterior that is added. So this allows us to make a huge simplification. We can say, well, it really is just the difference between where you are and where you need to be. That's an error signal, and we call that S. And we divide that by a noise scale, N. And now we get a signal-to-noise ratio, and not just that, we get half the signal-to-noise ratio squared. Now, this is called the surprise potential. So it gives the KL between the observation likelihood and the goal prior. So what's interesting about that is that it's also exactly the same form as the potential energy of a Hookean spring. And you see how these two equations are similar in the left. So all we need to do is read out on a latent variable S what the surprise is. And you can think of the negative log evidence as being on the y-axis of that. And so instead, we optimize to zero. We go all the way towards the zero of the likelihood function, the negative log likelihood. And we ignore the partition function in this case, which is the added constant at the end. What this does is it gives us a threshold acceptance. We can go from a signal to noise ratio to another signal to noise ratio and traverse part of the parabola. And depending on what part it is going to be a fast part or a slow part. The slower is towards the bottom of the parabola. The threshold is defined as some multiple of the variance of the parameter of the parabola. Sure, I should say standard deviation. Why is that? And we'll see that in a bit. It's because otherwise we change the shape of the parabola in order to express a threshold. And what we want to do instead is just traverse part of the parabola so that the actual equation stays the same. So what this yields in terms of Bayesian updates, and as I said, we don't really need to look back at normal distributions, but I'm going to do it anyways, is that as we traverse or do a gradient descent on this surprise potential, we can get into a position where we halve the error every time interval. And this is a really elegant thing. It means that basically we can process bits, a bit being defined as having the normalized error. And we can keep doing this until we reach a certain threshold, at which point we stop. And this is essentially just energy dissipation. We're going from a high energy potential to a lower energy potential by dropping the voltage. All right, so what does this have to do with human-computer interaction? Well, we're going to apply this in two ways. First of all, we're focusing on actions, and the canonical action in human-computer interaction is the hand movement. And the hand movement was modeled by Paul Fitts in 1954 with the Fitts law experiment. So we're going to examine that and see if Fitts law emerges from a gradient descent on a Hookean surprise potential. And then the second thing that is important is decision making. And this is modeled using Higgs law, which was done in 1952. And we're going to see the same thing, see if we can just use this simple Hookean surprise potential and see if Higgs law emerges. All right, so we're going to start with movement. Now, why is this relevant for human-computer interaction? You might have been encountering situations where you have tiny buttons or where you have to move up and down, particularly on iPhone in email. You have to compose an email and then send it at the bottom, compose it at the top. And of course, these buttons are tiny. So which design would be better? Well, of course, the bottom design, but also the design with the bigger buttons. And this follows from Fitts law, which basically says if the distance is further away, then you need to also make the button bigger, and that relationship is logarithmic. So this is what a Fitts law experiment looks like. You're basically clicking between two targets of a width W and an amplitude A apart. And what we're seeing here is that the uncertainty in the posterior uncertainty here is actually expressed in the velocity of the cursor here. You see that as a little normal distribution that is indicating the velocity there. But there is also a prior goal, which if we click on these, if we execute this experiment lots of time, we actually get an endpoint distribution that's sort of like a Gaussian over that goal. This is not necessarily our goal precision, but it is somewhat related to that. The movement time analysis that comes out of this follows the following form. The time is a linear regression to a logarithm, which is really the number of choices, so the number of binary choices that you're making in finding the target plus one. Why the plus one? Because the target itself needs to also be taken into account. And this is lovely because it works quite well with our view of how energy potentials might function. Now, the B here is important, so I want you to remember the B. We're going to use it later. The B is basically the slope of this logarithm, and it tells you how much time impact there is for every bit. So it's the time per bit. And if we reverse it and take the reciprocal, we get bits per second. And guess what? We're going to use that as our learning rate in the gradient descent down our surprise potential. But 1 second. Here we see the logarithmic relationship. We see movement time on the y-axis and the number of choices on the x-axis. And the b typically in these Fitts law experiments are somewhere between something like 200 and maybe 400 milliseconds. So we can express about 4 to 8 bits a second. It depends also on the line you're using. And if you wondered how it's possible that your mouse works so well or that the stylus that you're using is so fantastic, it's because scientists have been doing this kind of experiment for a long time, trying to find the optimal bit rate for a device. So the optimal bit rate is not just something that is a function of the brain, it's a function of limbs, and it's also a function of throttles. For example, if you add a mass to your hand, you get a different rate, or if you use a different input device, you get a different rate. And this is called the Shannon-Hartley equation. It basically models, it's a very old theorem from 1947 that basically explains the capacity in bits of an analog channel being the logarithm of the number of choices you're sending through that channel plus 1. All right, so how does hand movement work in bit space then? Well, first, we process the highest bit. So we're having the biggest distance here, and then we keep doing that until we hit the target. And the question is, does this follow the surprise gradient? So binary search is, in fact, linear in log space. So this fact of having the distance actually leads to logarithmic time automatically. Also recognize that this implements a Bayesian update to a goal automatically, where the size that we're modeling is the size of the threshold plus the size to the threshold. And the threshold here is defined as some Z ratio times the precision of the task. And the precision of the task is set in the beginning as you're practicing for your targets. And it tends to be set towards the smallest target, but then maintained throughout the experiment. So if we compress this into bit space, we now see we have linear relationships, and all we need to do is multiply this with the time per bit. Each decision takes the same amount of time. And so we go from a fast movement to a slow movement. Now recognize that the slower bits, therefore, are the ones that cost the most time, which means that if we have a more precise target, we're not adjusting the slope of our surprise function. We're just going towards the bottom of that surprise function, and this costs more time to be precise. In doing so, we obtain a relative information game. And you see this on the right. We're diminishing surprise. This is following some kind of Hookean spring, which you see in the surprise function. And we're moving from the number of choices plus 1 to the choice that we want to have, which is Zn. So what's cool about this is that if I normalize everything to number of choices and I set the scale to n, now it really doesn't matter anymore. My surprise function is always going to be looking the same. So if I, for example, divide 80 pixels by 20 pixels, it's the same as 800 pixels over 200 pixels, or 8 choices over 2 choices. It's all the same thing. It's 4. All right. The way to think about the relative information gain is that because we are halving the distance, we can apply a logarithm. This logarithm goes from the distance plus 1 to the 1, which is where 1 is defined as Zn. And so we can subtract those two logarithms, which becomes a division. And of course, we can then solve for this to be the starting position over the criterion, which in Fitts law is A over W. So I'm going to show you how this works. So first, I'm going to show you how you can think of this as bits traveled. So we start somewhere, let's say at 16, and we're now 8, 4, 2, and we're finally at 1. Now, if I change the size of my target, it'll complete much faster because it only has to do 2 updates in this case. Now, of course, the hand will still move towards the middle of the target, but we're not really modeling that. We're just thinking of it as an information problem. So the whole idea here is that surprise is actually the same thing as potential energy. Just as you have to climb up a mountain in order to throw yourself off it when you're in a wingsuit, you have to have the thought in order to have the action. And in fact, maybe the two are actually the same. So movement is controlled through variational beliefs update in binary space, searching for the target. But the surprise is the potential energy guiding it, and the gradient is the force driving the work. And so we set about to see if this works in Fitts law. So we did a Fitts law experiment. And to do so, we need to take a variational mechanics interpretation from physics. So the Lagrangian basically says that the total energy is always going to be the same. And it's given by the kinetic energy, which is half mass times the velocity squared, minus the potential energy. And so these two basically juggle. And you see this when you have a pendulum. You see it literally juggle between potential energy and then it stops. So all the kinetic energy is in the potential energy, and then it goes faster, and it'll move fastest actually at the bottom, where all the energy is in the kinetic energy. So we can use this in order to solve our function. Now, the idea is the hand is actually literally pushed along by the force, which is the gradient of u. So if we look at the experiment, we look at the kinetic energy, we get these kinds of velocity profiles. Now, this may not mean very much to you, but we're basically changing both the distance and the size of the target. And what we're seeing, if we normalize for distance, we see that these are all the same. There's a bit of clipping that occurred because of a bug, but other than that, these look very similar. And so the question arose, can we indeed use just one surprise potential? And the only thing we're changing here is that we're reading a different segment of this surprise potential rather than change the curvature. Why can't we change the curvature? Well, we think of this as a spring mass system where the curvature is the k or kappa. This would change the precision of the surprise function. We could change it by, for example, the size of the target. But this goes exactly opposite to what we see in Fitts law. Smaller targets take longer than larger targets. And of course, if you were to do this, your surprise potential would become faster for smaller targets. So this is not how it works. So instead, we're keeping a simple half number of choices squared surprise potential, and all we're doing is taking the gradient of that and then changing the segment on which you go towards the noise floor n. So this makes n a geometric scaling factor. And so the second trick that we're doing here is we're saying we're separating the time dynamics from the geometric dynamics. So this just tells you how much energy there is in the landscape. And we then roll over that energy through time, dissipating that energy using a different learning parameter, which is our 1 over b. We'll get to that in a second. What's cool about this is that u is dimensionless. It turns any variable into number of choices, and you could use u for pretty much anything. Now, what this function does is you get exponential decay until you hit that criterion of Zn when the error hits the noise floor. And thus, we get emergent logarithmic time evolution. So we need to apply the Euler-Lagrangian to the Euler-Lagrange equation to the Lagrangian. And we also need to add dissipation. Why? Because unlike a pendulum, we don't conserve energy. We lose energy quite quickly because we want to stop towards the 0 point of the action. So we add a Rayleigh constant, and that gives us an Euler-Lagrange equation, which is basically telling us to do a double derivative to get the acceleration, and then a derivative to get the displacement of the displacement, I should say, and then add a velocity damping factor as well. And that yields this equation. Now, important is that because we're using normalized error, we can actually redefine this error as small s. Why? Because then we don't have to deal with this variance thing anymore. We can just say, well, we have divided s in n number of choices or steps, and this is what small s represents. And we can now take small s into this equation, which gives us the acceleration, critical damping, and the Hookean derivative of u, which tells us that there's some factor of displacement as well. Together, these need to add to 0. Now, here's the leap for the k here, the kappa. We are choosing to use the bit rate that we found in the Fitts law experiment. So we're taking the b, taking the reciprocal, squaring it, and then we're applying the regular 1 over b as the critical damping factor. And that gives us our final equation here that you see at the bottom, where we have 2 over b as our critical damping factor, and we have 1 over b squared as our spring constant. And so what this tells us is really how fast you're moving down this geometry that is created out of number of choices. So this gives us the, if we rearrange this equation, we get acceleration equals 2 over b v minus 1 over b squared x, where x is the displacement, should actually be s, which you see on top. Now we know a. Why? Because we're reading a from the surprise potential. We just take the derivative, and that's our a, and that means we can solve the rest of the equation. We do that by basically taking tiny time steps. So we take a time step of 1 millisecond, that's our delta t. We multiply our acceleration with delta t. That's like taking a derivative, ending up with a velocity, and we can add that to our current velocity. So our current velocity starts at 0. We read a high force out of the surprise function because we're far removed from equilibrium. We multiply by 1 millisecond, we add that, and we keep doing that. Then each step, we do the same thing to derive x from our velocity. We multiply our current velocity by delta t, which takes a derivative, yielding x displacement. We do this n times. We count the number of times we do this, and that's the number of milliseconds that the movement takes until it reaches a threshold, which I didn't express in this equation. All right, that looks something like this. So here we see what happens when you take the second order. This is a bit much. Here we go. We literally see this kind of pendulum-like action. Now, if we add dissipation, we see that it really moves to 0 and it just sticks there. It's like putting peanut butter on a bowl and rolling this mass towards the bottom of the bowl. Our empirical results look like this. This is a log linear fit, so it looks linear, but it's actually logarithmic. And what we see at the x-axis is the number of bits of difficulty, which is basically our relative information gain. The b we find here is 0.231. We're going to ignore the a for now, but look at the fit. It's almost 100%. It's 96%. So this is our empirical participants following this task and then taking sort of the average of that and seeing what their bit rates were, or rather the time per bit. When we run the simulation, dropping a little heavy ball down the surprise function, we get almost exactly the same number, and we get an R-square of nearly 0.9. So what that tells us is that there is this clear relationship between lowering your surprise and the logarithmic function, which is given by the exponential gain that is produced when you are having the error. All right, how about decision making? Well, we can do the same thing. Hicks law, here we have 1 choice out of 8, or 1 choice out of 4, or 1 choice out of 2. Again, we get a response time that is very, very similar. It's a logarithm of the number of choices. And so here's what that looks like. We can actually model this as potentials that are running down the surprise potential. And one of them, in this case, hits the threshold first. And this is a way to make decisions. All you need to do is have them have a different energy, drop them down to the surprise potential, and they sort themselves. It doesn't matter if you have 10,000 decisions to make or 2 decisions to make. The one that crosses the threshold first wins. All right, so for this one, we don't need to do the whole second order equation, we can just do a first order dynamics. And so all we need to do is say the velocity is equal to the negative displacement times this learning rate. This produces an exponential shrinking of the normalized error over time. So for each time unit, if we then solve for time, we get a natural logarithm, which we can convert into the type of logarithm we see in Hicks law. The empirical results are very good. An R-square of 97%. We see that the B is 87 milliseconds. If we then look at the results that we get when we simulate this using a surprise function with a gradient descent that's just first order, we get 89 milliseconds. Now, the A here is not modeled. Why? Because the A is the actual moment from making the decision to activating your motor neurons and actually pressing the button. But we can actually simulate that too by using a neuron that actually inflates its error. All right. So that means we could probably also, most of what you saw here was variational free energy, but we could probably also model expected free energy this way. So the simplification here is we just simulate each possible action as a surprise trajectory. Each has a potential, and we do the argmin, and the one that hits the threshold the first is the one that has the highest likelihood of working. And so EFE becomes less about computing future beliefs and more about comparing how quickly actions dissipate surprise. Now, one key reason this is possible is because we're using normalized error. All right, that's it for today. That's all I have time for. So concluding remarks, interactive inference simplifies active inference for interaction design by using normalized error. It's a signal relative to noise that becomes dimensionless, and it also plays really well when we're looking at the Shannon equation. A canonical quadratic potential links the KL divergence, the negative log likelihood, and Hookean energy, just unifying three different fields. A parabolic segment of this invariant damped spring potential is what we traverse in order to go from error to solution. Variational free energy then unfolds by relaxing the surprise towards that task-defined noise floor. And if we then look at the time that takes, Fitts law emerges. To make decisions, it becomes a competition between simulated surprise trajectories, and Hicks law emerges using just a simple first-order relaxation. So with this, I'm hopeful that usability becomes efficient surprise reduction through better designed energy landscapes. And these energy potentials become the generative models in a least action Lagrangian formulation. With that, I'd like to point out the paper, Interactive Inference, a Neuromorphic Theory of Human-Computer Interaction. It's on arXiv. It will be published in the Handbook of Human-Computer Interaction by Judy Jaco, end of this year, somewhere in September probably. You can scan the code in order to get a PDF. I wanted to thank you for listening. I'm happy to take questions, of course. And I wanted to thank Zaf Fountas for, particularly in the beginning, helping me understand the concept of the principle of free energy. Thank you very much.
Great. Thank you so much, Roel. Okay, we have some time for questions now. So if anyone has a question, please raise your hand or just speak out. I did have one question. So in the case for Fitts law with the motions, what's the relationship between what you're describing and, for example, learned reflexes? Because if I understood it correctly, this law depends on, as you're moving a cursor or your finger towards a position, you're reevaluating at each step, right?
Yeah.
You necessarily have to be able to take feedback at each step as you halve that distance. But do you not have the intuition that maybe for the mobile phone, you're so well versed in making these small actions that you're doing them almost directly, like when you make eye movements and you're able to land precisely on the target in a single saccade.
Yeah, no, there's a big distinction. So when you make a hand movement, you will always produce logarithmic time. You will always be reducing the error in this way, and that's because hand movements are slow enough for your brain to make the mapping between observation and state. So it's not just your eyes following your hand towards the target. It's also proprioceptive feedback, and it all gets computed into how far away am I in terms of unitless error. Um, Whereas with the eyes, you're right, it is more of a reflex. Why? Because the eyes are directly mapped to a coordinate in space. Because during an eye movement, the processing of the image is actually suppressed so that you don't get dizzy. This, by the way, is why chickens do this when they walk. They don't do eye movement, so they do it with their head to compensate. So that means we can't really do a complete loop. So I think eye movements are better modeled by sampling, or if you talk in free energy terms, sampling of free energy and just jumping there. So eye movements have a very well-developed likelihood function. Now, where the likelihood function matters in hand movement is that you're really doing a Jacobian, right? So it's actually you're doing polar coordinates in order to get there. And this is really well learned behavior. And so I'm just going to assume in my model that that is perfectly learned behavior. And this is definitely a weakness of the model, is that we don't really talk about likelihood functions.
Right. Okay. Thank you. That's interesting. If there's no other questions for the moment, then we can hand over to Carl to give
All right.
some feedback.
I haven't finished my cigarette yet. Haven't you got another question to ask?
We can chuck
If
in
you
another
haven't,
one.
I will put it out
Um,
and join you on camera. There we go. Good, lovely.
Hi,
So it's my
Carl.
turn now. I will.
How are
Yeah,
you?
I'm fine, thanks. That was very impressive. Um, yeah. So yeah. Well, let me repeat. That was very impressive. I wasn't aware of this work. And also its applicability. Before I give you a stream of consciousness and what will hopefully be helpful endorsement, is there anything particular you'd like from us at the moment? Do you have any specific questions, or you just want to now, enjoy the feedback?
I'm happy to hear the feedback. Yes.
Okay, right. So, I mean, clearly you've got a lot of experience and a deep technical knowledge of the underlying mechanics here and its application, in a pragmatic sense. So, that's something which we don't have. But I can certainly see that if you can reduce optimal behavior to simple Lagrangian mechanics and motivate that from the variational principles of least action that underlie active inference and the free energy principle, I can certainly see that's going to be a very powerful way to apply the implicit dynamics. And I will just look forward to seeing how you actually implement that in in the real world. The, the other thing, Mash, I was intrigued with was your ability to recover heuristics like Fick's law and sort of 20th century descriptions of largely, I presume, inheriting from psychophysics as opposed to physics. Um, I think that in and of itself, if you had time or a PhD student, will be well worthwhile communicating a retrospective of 20th century psychophysics under variational principles of least action in the 21st century. I think that would be an academic exercise, but I think it would be something that you could get somebody to invest time in doing properly. Something like physics of life reviews or sort of behavior and brain sciences or something along those lines. Because what was impressive to me, I'd never considered these things. I always assumed that if you stick to the right principles, you should be able to explain everything. But I haven't actually sort of thought about explaining everything, such as Weber's law and Fick's law and all of that good stuff. So I'm just saying that, that's a worthwhile agenda if you had time or colleagues to pursue that outside applications and industry or design, just to sort of go back and derive these laws from first principles, which effectively is what you've done. So that leaves really my feedback in terms of, from the point of view of the physics, giving you ways of simply motivating how you can get to the formulation that you have put forward without having to say we made this simplification. Because when you say that sort of people think, oh, he's only doing it approximately. My impression is you're actually probably doing it exactly under the Laplace assumption.
Right.
And
Yes.
I'm just, in terms of telling stories and writing papers, certainly for the academic literature and or the psychophysics literature, then I think you can sort of tell the story without say, well, we are going to make our life simpler by doing this and doing that. I may be wrong, but I think a lot of the simplifications that you used in terms of being able to use Lagrangian mechanics as the basis of active inference, or sort of solving Bernstein's problem, or however you want to solve it, and en route recovering all these the psychophysics laws could be done in a way which I think sort of mathematicians would find, or at least physicists would find, oh, I see, yes, he's that follows naturally from this. So my feedback, which is not going to be extensive, but and it may or may not be sort of hitting the mark, but what I was doing while listening to you was just picking out a couple of papers that say, yes, that makes sense. Having not thought about it deeply, but certainly, yes, I recognise that as exactly the right move. That could be sold as a simplification, or you could say under the Laplace approximation or under the Laplace assumption, it has to be the case that, for example, which would then put you in a very, very powerful position to say, right, under the Laplace assumption, then we can now derive Hicks' law, Fick's law, Weber's law, and all of that good stuff. And furthermore, there was, I think, a really interesting connection to theoretical neurobiology that appeals to information geometries, information lengths, information rates, and ultimately gauge theoretic descriptions of movement and belief updating. So I saw I know that you understand the maths, but I didn't hear you use the words like information rate, and if you can, you've also now got a story you can tell in terms of rate distortion theorem. You've got a story you can tell to the physicists like Gavin Crooks about the thermodynamics of information, read as belief updating. So I've got one paper that sort of really is just a hook to enable you to tell exactly the same story, but now using the kind of jargon that people in working in information geometries would recognize, and sort of join the dots for for those people who think about that kind of thing from that
I very much
perspective.
appreciate that. Yeah.
Yeah. Well, let me do that, and hopefully I will be reminded of all the thoughts that came to mind during your fast and furious presentation. So where are we? I'm going to share the screen. One thing just to sort of frame, let's go for share. One thing just to frame things, a distinction which came out right at the end of your talk that I think you might find useful is between two kinds of active inference. And one kind is where the priors over the trajectories or the paths that you're going to enact with your, for example, finger pointing or hand movements in this sort of your Euclidean space that within which our bodies move, comes in two flavors. And some people call it sort of mere active inference, and other people, as opposed to active inference with expected free energy. So from a maths perspective, these two kinds of active inference are discriminated or distinguished by the fact that the priors, which would be your goal distributions, over the trajectories, are specified explicitly for the movement in question. So there's no planning involved. Whereas active inference with planning, with intended behaviors, would call upon the expected free energy, which would have exactly that sort of Bayesian surprise, or at least expected Bayesian surprise, that KR divergence between your target distribution and your goal distribution and your predicted posterior distribution.
Yeah, I'm essentially, if I may, I'm essentially saying that a lot of those variables can just be learned from the real world. Or at the very least, the models of the real world that I have. Should I use a screwdriver or should I use a hammer? In this case, what finger, or what should I move my arm? Should I move my hand, or should I move my finger in order to hit the target? Is something that can be gleaned from the distance to the target as well as the size of the target. So
Yeah.
a lot of that can be learned from the real world.
Yes, and I certainly got that impression and concur exactly. And I think that nice discussion at the end about the difference between a pointing movement or a reaching movement that solves Bernstein's problem, and oculomotor behavior with saccadic eye movements really does, separate the two kinds of movement.
Yeah.
And everything that I saw makes me think that you're, if you like, lifting the essence of active inference into a world of application and Lagrangian classical mechanics in a simple and efficient way, applies to the first kind of active inference, which is exactly as you say, having a generative model of the physics of your body and just using that to attain fixed points attractors, where these attractors can be specified either with very precise bounds or less precise bounds, depending upon the task instructions or the intentional set of the subject. It doesn't. What I'm saying is, I think you'd simplify your story and account if you left expected free energy out of the story at the moment.
Right.
And the reason I suggest that is that when it comes to practically deploying the two different kinds of active inference in real world artifacts, say, for example, in drone research or autonomous vehicle research, the way that you put them together is that the planning part, based upon the expected free energy, is usually articulated under a discrete state space model, usually a partially observed Markov decision process.
Right.
And what it does is it provides discrete fixed points attractor intermittently. And then your kind of technology, the mere active inference, as it were, now just picks that up and then works out, okay, I've got to put my finger on that button in the next 750 milliseconds.
Yeah, may I comment on that? So I agree with you, and much of this talk is actually focused on phi. The reason I mentioned expected free energy is because, well, expected free energy is a complicated topic, and it's certainly complicated from a human-computer interaction point of view, because if you have a loop where you have to make a decision all the time, then from the point of view of making a fluid execution of a task, it becomes problematic.
Yeah.
But I think that the point I was trying to make is that what's really beautiful about this model when it comes to decision making is that we can think of a decision as parallel tracts of surprise that are suppressing neurons firing. And when surprise is low enough, the neuron reaches threshold and then the action gets taken. And so Higgs law seems to be modeled by that. It's actually what I'm describing is the A. in Hicks law that I did not model. It's the charging of the neuron and then subsequent actual physics of pressing the button and latencies involved in that. But it's also a very nice way to sort. If you charge the negative log probability into a surprise potential and you drop that ball, the one with the lowest potential will always win. And it doesn't matter if you have 1,000 of these, 10,000 of these, or just two. And so it struck me that that would be a very elegant way to make a decision based on however you calculate, that negative log potential, to make that decision of I'm doing this.
Right. Yes, I'd forgotten about that, which again is a very compelling story, and certainly makes a lot of sense when dealing with long horizon planning and you're doing a tree search and
Yeah.
you're taking the path integral. And of course, if you comply with the principle of least action, then that it is going to be a race to bound, literally, kind of process, which where the path integral here will be an expected free energy if you're planning this in the future. I'd forgotten about that, and that's certainly so. So that was Hicks law, was it? That was
Hicks law. Yeah, yeah,
yeah. So in my head, I didn't have find time to find an appropriate paper, but I was reading that in the context of race diffusion models and race to bound models in evidence accumulation.
For sure.
So which wouldn't involve planning because that would be more sort of committing to a particular posterior and a set of models.
Yes, yes.
And yeah.
Well, what I'm essentially saying is that if, let's say, we keep this to the execution of a variational free energy pattern, so let's say we have a hand movement, I could simulate that hand movement in my mind and see which one reaches the threshold or crosses the threshold first. What I'm essentially saying is that doing that is very similar to just doing a direct Hicks law decision,
Yes,
which is
yeah,
triggered
but
by
that story would certainly require you to go into planning and expected free energy. Absolutely.
Yeah, for sure,
Yeah. No, and it would be in the continuous domain in this instance. I think because you want to use the physics of the generative model to get the posterior predictive to evaluate the expected free energy to get the time to bound. So you. It's just the literature on expected free energy for continuous state spaces is less developed than it is for discrete state spaces. But yes, you're right. That you should certainly tell that story. There is some interesting work in robotics coming out of places like Delft University and the work of people. Tim Verbel used to be at Ghent has also done quite some interesting work on that. And I think the yes, I think it is again Delft, but I may be wrong. The RX Infer team, not Bert Kappen, the team doing the reactive message passing have also looked at.
You mean in Eindhoven?
Yes, I think so. Yes,
Bert de Vries.
Yeah, Bert de Vries. Yes. So I think that Bert's done some of the. I got confused because Bert Kappen's with you, isn't he? Yeah. So yeah, Bert de Vries. I think he's done some of the best work in continuous state spaces. So it may be that's the kind of expected free energy planning as inference sort of frame where you can take it. Having said that, I think it's also important to mention that this is very distinct from the kind of way in which you could actually combine discrete active inference with the procedure with the mere active inference that you've already established before moving on to Hicks law. And I'm thinking again of saccadic eye movements because as you say, in the real brain, you're basically integrating a whole series in parallel of potential futures, all entailed by the fixed point you're going to fixate at. In salience maps, probably in the deep layers of the superior colliculus. So you've got this parallel processing that some people write down in terms of bumper tractors,
Hmm.
where you're doing a path integration into the future
Hmm.
until the winning, if you like, bump on the
Hmm.
salience map in the superior colliculus reaches a threshold, and then you trigger the saccade. But of
Hmm.
course, the actual execution of the saccade you can now do using your technology. So
Hmm.
you're just using the expected free energy read as in parallel, evaluated over all possible places I could end up looking, um, as basically supplying the goal for the next continuous movement.
Yeah.
That's what I was trying to get at in terms of separating the applications, which
Yeah.
is distinct from actually selecting a number of continuous paths into the future and using the path integral or race to bound um, technology to actually select the next continuous movement.
Right.
So
Yeah.
there are a number of ways I think you can sort of either demonstrate or at least describe the potential applications of this. Do make the distinction between using expected free energy to provide discrete fixed points that your
Hmm.
continuous scheme can now attain and
Hmm.
realize, versus actually using what you're suggesting, which is using path-integral formulation on continuous trajectories in the future, using expected free energy. Yeah, okay. Well, I'll leave you to do that. Do you know Bert de Vries? Is he?
Yes, yeah, I met him. He gave a talk here not too long ago.
Okay, he does a lot of work, but if you just ask him specifically about his work on path integrals of expected free energy and the kinds of bounds that the way that he solves a problem, you may, he might send you a paper that says, "Oh yes, I can do this in a really simple way if I," and then um, and then you can make a friend or preempt him or whatever. Anyway, back to my sort of more technical contribution. May be wrong, but if I was trying to paraphrase the importance of using normalized error, and I was trying to explain to somebody who was deep in the weeds of variational free energy, um, I would say something along the following lines: that under the Laplace approximation, where the functional form of all your belief structures in log space are quadratic, that simply means that your free energy gradients can always be expressed as a prediction error. Furthermore, it's going to be a precision weighted prediction error. So what's a precision weighted prediction error? Well, it's a normalized error. It's normalized by effectively
Hmm.
the inverse variance. And this basically means I can rewrite the whole calculus in terms of standardized errors, which you will find in the um, neurophilosophy literature described as precision weighted prediction errors. So what I'm saying to you, there's already a rhetoric out there
Right, right, right. Yeah,
in the non-technical literature
yeah,
where
yeah.
people just think in terms of minimizing precision weighted prediction errors. But what is, if a precision weighted prediction error um, um, is just a normalized error, then it is also exactly what people use in statistics. So a t-test
Yeah,
is
yeah.
the gradient, the error, the difference between my null and alternate hypotheses and the group mean, divided by the standard error, which is just the precision weighted or normalized. So a bit like Z scoring. I think you've got this really common theme here. I think that would be very useful because everybody understands why you have to use normalized prediction errors in statistics, such as log odds ratios under Gaussian assumptions, which is a definition of parametric statistics, getting the t statistic as the normalized error. But people may not realize that the precision weighted prediction error is just the same thing. So I think it would be a useful join the dots between statisticians,
Mm-hmm.
the predictive processing community, who largely comes from well, philosophy, but they're also quite skilled in neuroscience, but they're not terribly skilled mathematically. And then your engineering computer science approach, where
Mm-hmm.
just saying that the central object, the simplest thing, and the gift of the Laplace assumption, namely a quadratic potential energy landscape, is that you can write everything down, the whole calculus, in terms of these normalized errors or normalized gradients.
Mhm.
And of course, you're in log space, and that gives you basically access to all these 20th century psychophysics heuristics.
Mhm.
Simply because you've made this second order approximation. And then you can say, well, we could call this Laplace approximation or Laplace assumption, but we could also say it is just the first non-trivial Taylor approximation to any universe.
Yeah, exactly.
And so you can really sort of push the generality of this. Not that I'm really committed to a Gaussian assumption or parametric statistics assumption. I'm just taking the first non-trivial, the first non-trivial Taylor approximation to any generative model, to any universe. And I think that sort of, if you like, makes you sound slightly less humble in terms of, well, if I simplify this and simplify that, I don't think you need to do that. I just say, and it really does clarify exactly what is on offer here in terms of it's just the first non-trivial low order approximation to physics.
Mhm.
And if you think about it, Newton's laws of motion, all Lagrangian Hamiltonian mechanics basically use exactly the same
Mhm.
assumption. And furthermore, you know, with a couple of exceptions, most of quantum mechanics of the sort of Schrodinger wave equation kind usually assume a quadratic
Mhm.
potential, to actually get a feel for deriving things like Heisenberg uncertainty principle. So I'm just counselling that you just highlight the generality of the second order approximation everywhere,
Mhm.
just as a way of sort of asking people to commit to getting into that. Another gift of the second order approximation is that under the imperative, the maximum entropy principle, for example, the Gaussian distribution has the greatest entropy if you're just allowed to supply two sufficient statistics. So the Gaussian approximation or the second order approximation is not just a second order approximation, it is the optimal assumption according to E.T. Jaynes and all of measurement physics.
Mhm.
Under the constraint, you've only got a low order approximation to the sufficient statistics, or you only have access to the first order sufficient statistics, namely the expectation. The beautiful thing is that the second order, the conditional covariance or precision of your Gaussian assumption now becomes an analytic function of the mode or the mean.
Mhm.
And that means you don't have to represent or evaluate it explicitly. And in particular, if you're assuming equal precisions, which you were doing at one point in the derivations, um, you, um, you, you certainly don't have to evaluate it, but it exists. It
Mhm.
exists as an analytic function of the mode. And that's because the functional form allows you to minimize the variation free energy with respect to the precision conditioned upon the mode.
Mhm.
And that's basically the point of this paper, which is why this is so this paper is written for statisticians a long time ago now, over a decade ago, but its main point is basically that there exists an analytic solution to the precision that you're going to use to do the normalization um, from the mode, which means the only thing you actually physically need to represent or encode is the expectation. It is
Right.
the mode that you were showing in those lovely graphics, and you're making your life even a little bit more easier by assuming that all the likelihood and the prize have the same variance. That is a bit of a strong assumption, but I wouldn't worry too much about it. Um, um, if you didn't make that assumption, you could point out that it would be trivial, should you want to actually derive the precisions from the mode. So you just need to get the dynamics of the mode, and they're just a gradient descent on this normalized error, because the error is the free energy gradient. again, in virtue of the second order approximation of the Laplace assumption. So I thought that might be useful. I mean, just as a footnote or a point of discussion.
Definitely, yeah.
The variation Laplace, which is what we call the application of variational principles of least action under the Laplace or second order assumption about the functional form of the densities. The special thing it offers is you can articulate everything in terms of the first order, a single sufficient statistic, which is just the mean or the expectation or the mode. And that's why it's so efficient, certainly in my world. So I thought that might be useful as if you like, a further explanation to people, again, in the weeds with variational free energy, why you are focusing on this one normalized small s, as it were. That's all you need under the second order approximation.
Yeah, thank you. That's very useful.
The other thing I liked was you're sort of trying to engage